9th Standard ICSE Chemistry, Chapter 1, Language of Chemistry. Textbook name is by Anita Prasad. Introduction can be cancelled. Mark the definition of chemistry. Notice how we use symbols for the various elements in chemistry. For some elements, we use only the first letter. For the others, we use two letters. For example, C is already being used for carbon. So for chlorine, we use Cl. For some substances like sodium, we use the letters from their Latin name, natrium, so Na, because So might be the element symbol for some other element. Formulae are words that describe the composition of the myriad substances, various substances that surround us. NaCl is sodium chloride, CO2 is carbon dioxide. Equations help us to understand the relationship between the reactants and the products. Now, the fundamental discovery of the atom was made by many scientists, but the Dalton's atomic theory is the most popular. So learn these points, unless your school teacher cancels this. These two paragraphs mark it as read, which means that you can read it for general knowledge, but no question will be asked from here. However, I'm not cancelling it. It's good to read it. Now, he said that matter is composed of very small, indivisible particles called atoms. This is proved false now because atoms can be broken down further into subatomic particles like protons, neutrons, and electrons. All atoms of a given element have identical properties, but each atom of an element is different from the atom of another element. Now we know that even this is not accurate because atoms of the same element can also be different. Example, isotopes. Oxygen 16 and oxygen 18. They have the same atomic number, 8, but mass number differs because of number of neutrons being different. Atoms of different elements combine in fixed ratios to form compounds. This is true, and the compound has unique properties. The original components have lost their properties. For example, hydrogen is combustible and oxygen supports combustion, but when they react in a fixed ratio to form water, the water has completely new properties. It is neither combustible nor does it support combustion. In fact, it extinguishes fire. And a compound cannot be simplified or broken down into the components by physical means. You will need chemical means to break them down. Mixture components can be separated by physical means. Elements cannot be broken down by any physical or chemical means. However, elements can be broken down by nuclear means. Example, in a nuclear bomb. Now, atoms are neither created nor destroyed. Yeah, in chemical reactions they are not, but in nuclear reactions they are. But nuclear chemistry will be taught in higher standards. John Berzelius was the one who came up with the idea of using symbols, using the letters to symbolize each atom of an element. So when you write P, it represents one atom of phosphorus. K for calcium represents one atom of potassium. Mark the definition of atoms. All of this is just read. Mark the definition of elements as well. They are pure substances like compounds because they are made up of only one type of atom, one type of particle. Even compounds are pure substances because they are made up of only one type of particle. Mixtures are not pure substances. Currently, there are 118 elements and their names are decided by IUPAC, International Union of Pure and Applied Chemistry. Cancel this box, irrelevant. These tables have to be learned for knowledge of the symbols of elements. Notice how hydroargyrum is Hg, which is a symbol of mercury. Now N is a symbol of one atom of nitrogen, whereas N2 will be a molecule of an atom. It's a diatomic molecule. Molecule is the smallest particle of a substance, which can be an element or a compound, which does exist independently. An atom can be a molecule. For example, this is an atom of platinum, and it is also a molecule of platinum because it exists independently. O is an atom of oxygen, but it is not a molecule of oxygen because it cannot exist independently. O2 will be a molecule. So molecules can be monoatomic like platinum, diatomic like O2, triatomic like O3, ozone, and it can be tetraatomic like glucose is C6H12O6. Next, the definition of radical. It is an atom or a group of atoms of same or different elements carrying positive or negative charge. So for school level, you can just remember radicals as ions. So just like we have cations and anions, we have positive radicals and negative radicals. But in reality, radicals can be without charge as well, which you will study in 10th standard. Mark the definition of positive radicals and negative radicals, or cations and anions. The valency depends on how many electrons are lost, gained, or shared during a chemical reaction. It is the combining capacity of an element, but we'll mark the definition on the future pages. Earlier, it was defined as the number of hydrogen atoms with which it can combine. For example, oxygen can combine with 2 hydrogen atoms to form a compound. So we say the valency of oxygen is 2. Nitrogen can combine with 3 hydrogen atoms, so valency is 3. Carbon with 4 hydrogen atoms to form methane, so valency is 4. But now this method is not used because there are some elements which cannot combine with or displace hydrogen. And also, what if it combines with some other number of hydrogen atoms? For example, in hydrogen peroxide, H2O2, 2 oxygen atoms are combining with 2 hydrogen atoms. So then the valency of oxygen is not seen to be 2. So now we have a better definition. It is defined as the number of electrons lost, gained, or shared during the course of a chemical reaction. So you can mark the definition on the page number 5 here, definition. Types of radicals: simple cation, compound cation, because it has more than one elements. Simple anion and compound anion, because I can see 2 elements, chlorine and oxygen. What is an ion? Mark the definition: any charged particle is an ion. You see, if an atom loses electron, it becomes a cation. And if it gains electron, it becomes an anion, because an atom is neutral because the number of protons and electrons are equal. However, to achieve stability, to achieve the stable electronic configuration of the nearest noble gas, that is to complete its duplet or octet in the last shell, metals usually lose electrons and non-metals gain electrons. So now sodium is stable, 2,8, but it has 11 protons, that's the atomic number, and only 10 electrons. So it has 1 proton extra, or 1 electron deficient. So it acquires a positive charge. Givers are positive people and takers are negative people. I mean atoms. Chlorine, 2,8,7. To be stable, it acquired 1 electron from somewhere, probably from sodium. So now it has 17 protons, that's the atomic number. You should know the atomic numbers of the first 20 elements. And now its electronic configuration is stable, 2,8,8, like the nearest noble gas, which is argon, and this is like neon. But the price it has to pay is it has 1 extra electron, so it is now negatively charged. It has become an anion. So both are stable, but both are oppositely charged. Now opposite charges attract each other, so they're stuck together to form a new compound, sodium chloride. That's an ionic compound. Mark this first paragraph as a GR. Next definition is variable valency. There are some atoms, especially the transition elements, atoms, they exhibit 2 or more valencies, like iron can be +2 or +3. Fe2 plus is called ferrous and Fe3 plus is called ferric. This is because they lose electrons not only from the last shell, but even the penultimate or second last shell. You see, the rules of octet and duplet are valid or sufficient only for the first 20 elements. After that, the rules become more complicated, which we will study in college level. Here, in Fe2O3, the valency of oxygen is 2 and the valency of iron is 3. And by the crisscross method, we got this formula. Here, the valency of oxygen is 2 and that of iron is also 2, 2 plus 2 minus. And they got cancelled, hence we wrote the formula as FeO. You have to learn all these variable valencies. Nowadays, we don't use terms like ferrous and ferric. Rather, we write Fe Roman number 2 and Fe Roman number 3, which is easier to understand. Mark this section as a GR. We are explaining that the reason why iron has two valencies is because it can lose 1 extra electron very easily. It doesn't make much of a difference for it to lose 2 electrons or 3 electrons. So in case of elements when not much difference exists between the energies of the last 1, 2, 3 or 4 electrons, variable valency is seen. So only this last paragraph is a GR. And now this entire paragraph, mark it as read. Now you have to learn this entire table by heart, because when we do the crisscross method from the exercise, knowledge of all these valencies will be useful. For example, if we have to write the compound of ammonium nitride, so we just write the cation first always, ammonium. This is different from ammonia. Ammonia is a molecule, it doesn't have a charge. And nitride is N3 minus. Now we do crisscross. The subscripts remain as it is. The superscript is exchanged, but then the sign remains as it is. 1 goes here, but we never write 1. 3 goes for this, but there are 2 elements here, so 3 is for both of them. So we'll have to use brackets. So ammonium thrice nitride. So we'll do such practice when we solve the exercise. Next, chemical formulae. Mark the first sentence as the definition. And they've explained how the crisscross method works. So this table, we know it now, so mark it as read. Now how to name a compound. Cation's name always comes first, anion comes later. And typically the anion's name is changed from the element's name. For example, sulfur becomes sulfide, oxygen becomes oxide, chlorine becomes chloride. Metal's name never changes, only non-metal's name changes, which is quite discriminatory, but these are the rules. If you don't like it, write a letter to IUPAC. Learn all these names of various compounds. Now if they give you a formula and ask you to find the valency of the metal, then notice that in MnO2, you might easily think the 2 came from Mn, manganese, so valency of Mn will be 2. But hold on, oxygen's valency was 2. So if manganese valency was 2, 2 and 2 would have got cut and the answer would have been MnO. So that means the manganese valency was 4, because then I can do 2 1s and 2 2s and then do crisscross, then only I'll get the formula MnO2. So the valency of manganese in this case is 4. It's manganic, not manganese. And whenever you write the IUPAC name, make sure you write the variable valency in brackets for metals like iron, manganese, gold, because they have variable valencies. We don't write it for sodium, potassium, because they don't have variable valencies. All metals form cations. Can you name a cation which is not made up of metals? Well, ammonium and even hydrogen. Now notice the difference. Manganate is MnO4 2 minus and permanganate is MnO4 1 minus. Oxide is again 2 minus and peroxide is O1 minus. Now let's study how to name acids and bases. First of all, mark the definition of acids. They are compounds which contain hydrogen as the only positive ion. For example, in HCl, H plus and Cl minus. So that's the only positive ion. So that is why it's called an acid. Why is the word only important? Because if I write, let's say, sodium bicarbonate. Now here carbonate is an anion 2 minus. Hydrogen is a cation 1 plus, and even sodium is a cation 1 plus. Even though it has hydrogen positive ion, it is not the only positive ion. It has sodium cation also. So we can't call this an acid. It's actually an acidic salt. It does have acidic properties, but it is not exactly an acid. Now binary acids, they contain halides. So along with hydrogen, they have just one more element, typically a halide or sulfur. So these are the examples you have to learn. H2S is hydrogen sulfide. When dissolved in water, it forms an acid called hydrosulfuric acid. Dissolving in water is very important for it to behave like an acid, because water can break the bond and release those hydrogen ions, which is the identity of any acid. The blue litmus turns red because of the hydrogen ions, more specifically hydronium ions, but that is intense standard. Now remember the names of the various acids. Sulfurous acid is H2SO3, sulfuric acid is H2SO4, nitrous acid is HNO2, nitric acid is HNO3. Also remember the names of these compounds. Perchloric, because it has 4 oxygen atoms. Chloric acid, 3 oxygen atoms. Chlorus, little less, so 2 oxygen atoms. And hypochlorous, hypo means even lesser, so only 1 oxygen atom. And these are the name of the anions, oxoanions, oxanions. These are oxy acids because they have oxygen also. These are binary acids, they don't have oxygen. These are oxy acids because they have 2 elements plus an oxygen atom. Bases are oxides or hydroxides of metals or ammonia, which contain the hydroxyl group as the only negative radical. So here sodium is a positive radical and hydroxyl OH minus is a negative radical. So it's the only one which is negative, so it is called a base. And typically the hydroxyl combines with metals, cations. However, ammonium is a non-metal, but still it is a cation. So even this is a base. Now those bases which dissolve in water are called alkalis. So out of these, 1, 2, 3, 4 are alkalis, although magnesium hydroxide is only partially soluble, so it's a weak alkali. Aluminum hydroxide does not dissolve, it will form a precipitate in water, so it is just a base, it is not an alkali. Now, there are some complex compounds which can be named like this: copper, tetraamine, sulfate, also silver, diamine, chloride. So you have to learn these two names because they will reappear in 10th standard. Next, chemical equations. Mark the definition, the first sentence. This is entirely read. We know all this. These are some examples, so learn them. It's IMP. In exam, they can ask you, give an equation, an example of an equation with 2 reactants and 3 products. So you can write this answer. Remember, it should be a balanced equation. You can write some other equation, but it should be a valid one. In the future, you will learn about observations also. For example, when lead nitrate is heated, it decomposes to form lead oxide, which is buff yellow or rust yellow when hot and yellow when cold. It also gives a reddish brown gas, which is nitrogen dioxide, which turns green acidified ferrous sulfate brown. And oxygen is a colorless gas which rekindles a glowing splinter. So all these observations are not a part of this chapter, it's a part of chapter 9, practical chemistry. Now, what information can we get from a chemical equation? Well, we can know the state of the matter, like solid, liquid, gas. We can know its concentration, if it's dilute or conc or aqueous. If it's a down arrow, it means it's a precipitate. Up arrow means a gas. Reversible sign means it's a reversible reaction, which means the products can again combine or decompose to get the reactant. But there are some things which we cannot figure out by looking at a chemical equation. For example, the rate of reaction. Just by looking at this, we have no idea how quickly will this reaction take place. For example, the first one is a fast reaction, but the second one is a slow reaction. So learn the information conveyed by chemical equation. We know the reactants, the products, the number of atoms of each element taking part. The balanced equation also gives us a number of molecules participating. We can also figure out the masses required for a reaction. For example, here, if you know the atomic weights, we can even know the gram atomic weights. But the total mass of reactants will always be equal to total mass or weight of products. In chemistry, mass and weight means the same. Why is this important? Because only then will it comply with the law of conservation of mass. In a chemical equation, there is no loss of mass. In a nuclear equation, of course, there will be. And the mass will be converted to energy, as given by the formula E is equal to mc squared. Now, why is it important to balance the equation? Because if you don't balance it, then again, it will not comply with the law of conservation of matter. If I don't write the 2 here, and 2 here, and 2 here, then there's a problem, because then there'll be only 2 hydrogen atoms on the LHS, but 3 hydrogen atoms on the RHS. How is that possible? The skeleton equation does not have balanced numbers. A balanced equation will have the coefficients so that it complies with the law of conservation of matter. So mark the first sentence as a definition and the second sentence as a GR. Looking at a balanced equation, we can also figure out the volume of the gas being produced, which we'll study in 10th standard. Now, this is just read, there's nothing to learn here, nothing can be asked from here. Now they're explaining to us how to balance equations, but we know how to do that, and we'll study this by practicing balancing from the exercise. So this entire page is just read, not important, not to learn. Next, even this is entirely read. Even from here onwards, everything is read. It's just examples of how to balance equations, which we'll study in a numericals video separately. Now, there is a trick here. When you write equations, make sure that these gases are written in a diatomic state. And also the elements are balanced in order of increasing frequency. So if 2 elements occur with the equal frequency, metallic element is balanced first. Try to balance oxygen at the end, oxygen and hydrogen. Next, atomic weight. Cancel the first paragraph. Now, how to calculate the atomic weight? This is the definition. Now, you may think that atomic weight is nothing but the number of neutrons plus protons. Yeah, but scientifically, it is calculated in a more technical way. We have a unit called 1 AMU, 1 atomic mass unit. And the relative atomic mass is the number of times the atom of that element is heavier than that 1 AMU. But what will be that standard unit of 1 AMU? Earlier, we assumed that 1 hydrogen atom will be 1 AMU, but it didn't work. Actually, the mass of hydrogen is 1.008, not exactly 1 AMU. And the reason why we are using AMU and not gram and kilogram is because gram and kilogram will be too huge to measure the weight of an atom. It will be like 0.000000000, many zeros and then 1 gram. So we need a smaller unit called atomic mass unit. And the standard 1 atomic mass unit is 1/12 the mass of a carbon-12 atom. So a carbon-12 atom's weight is exactly 12 AMU, fortunately. So we took 1/12 of that. What is 1/12 of 12? 1. Hence we use that as a standard. So the definition is the number of times the atom of the element is heavier compared to 1/12 the mass of a carbon-12 atom. The definition given here is simpler, so you can learn that. Similarly, learn the definition of molecular weight, also called relative molecular mass. That is, the number of times a molecule is heavier than 1/12 the mass of a carbon-12 atom. And instead of AMU, if we measure it in gram, we call it gram molecular weight. For example, calcium carbonate. The atomic weight of calcium is 40, carbon is 12, oxygen is 16. We don't have to remember this, it will be given in the question. So if I want to find the molecular weight of calcium carbonate, also called relative molecular mass, RMM, I just add them up. There are 3 atoms of oxygen, by the way, so 3 into 16 will be 48. And after adding, it's 100 AMU. And if I write gram, it's called the gram molecular weight. Beyond that, we can even find the percentage. For example, out of 100 gram, how much is calcium? So calcium was 40. So 40 upon the total, which is 100 into 100%. That's 40%. So mark the definition of percentage composition and learn this formula. We'll use it for numericals in the future. And here are just examples of how to calculate percentages. So mark it as read entirely. So notice how they have first found the RMM of NaCl, 58.5. Then to find the percentage of sodium, it's 23 upon 58.5 into 100%, which is 39.32%. The atomic weights will be given in the question. But why is chlorine's atomic weight 35.5? Why is it in decimal? Well, this is because chlorine is has isotopes, chlorine 35 and chlorine 37. And in the nature, there is more of chlorine 35. Almost 75% of all chlorine is of 35 variety. So the average of those two tends to be shifted towards 35, hence it's 35.5, not 36. Even all of this is just an example, mark it as read. The exercise is entirely for homework. But the 4th and 5th question is numericals, so that has to be done in numericals book. Next, on page 115, we have a worksheet for chapter 1. That will be for homework in the future whenever I give the homework. You can do it there itself. Worksheet 2 has to be done in notebook, numericals book. So make a separate book for chemistry. Whenever I ask for it, carry it. Solved examples also need to be done whenever I give that homework. All these solved examples. Then there is an exercise of chapter number 1. Now here again, question 5 is a notebook, question 6 is notebook, question 9 is notebook. The rest are theory questions which can be just done here itself. You can write the answers here. Or if it's a big answer, you can write the page number and mark it there. And if you have any doubts, you mark it and ask me. Then we have exercise 2. This will be entirely marked as NB to be done in notebook. Then we have the evaluation test, self-evaluation test. So here, mark question 5 as NB and 6 as well. The rest of the questions can be done here itself. Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.